Hey guys, today we're going to be going over chemoreception of smell and taste, how we smell things, how we taste things, and kind of where it's located, what components are a part of that process. So let's start with taste. We've all heard of taste buds on our tongue. They help us taste things, right? And there's a few forms of taste buds. We have circumvallate, fungiform, filiform, and foliate. Circumvallate, it's going to have a large groove around the actual papillae of the before you get to the taste bud. Sorry, I misspoke. We have papillae, which are what we see on our tongue, and then in these grooves, so this is your papillae, and then there are grooves on the outsides of those papillae that lead us to the taste bud itself. So there's certain types of papillae. You have circumvallate, which large groove around. You'll just see a large groove around the papillae. Fungiform kind of looks like a mushroom, just a little bump for your papillae. Filiform is a string. It's more just like pretty skinny, but it'll stick up. Kind of looks like a paintbrush to me, at least, or a flame. And then foliate, leaf, shaped like a leaf, pretty straightforward. So that's just kind of the papillae that we're working with. And then on your outer sides of the papillae, in the grooves, you'll have your taste buds, and those are these dots that I've drawn. And if we blow that up and look at it in a bigger picture, we're gonna have this. So this is our taste bud. We're gonna have a ton of taste cells, and those taste cells are gonna differentiate between salty tastes, sweet tastes, savory tastes, sour and bitter tastes, and those are all of our tastins. So the taste cells will be specific to certain tastins. So these taste buds are surrounded by basal cells as well as support cells. Support cells separate your taste cells, and the basal cells are just kind of cushioning it too. On the ends of your taste cells, you have hairs. Those are your taste hairs. Those hairs will essentially grab onto tastins and help us stimulate the taste cells. So if we move over here, again, these are taste cells. They're just vertical this time. Let's look at our first taste cell, which will be specific to sodium chloride or salty taste. This cell will just have a channel for sodium, and if you allow sodium into the cell, you're going to depolarize it, and that's going to open up calcium channels and allow calcium to come into the cell. And if you increase intracellular calcium concentrations, then you're going to release acetylcholine, and then that's going to go into the synaptic cleft, and you're going to start an action potential. And that happens with all of them. So in general, if you increase intracellular calcium, you synapse, you create an action potential and send it to the brain. So for this one, this is going to be for a couple things. It's for sweet taste, for bitter taste, as well as umami or savory tastins. So these are all going to be G protein coupled receptors. So it's not like anything enters into the cell immediately, like with sodium, where it actually depolarizes and gets into the cell. This G protein coupled receptor needs a ligand to attach. And what that will do is it will send a signal throughout the cell such that you release calcium from your endoplasmic reticulum. You're releasing calcium from there. And it also can open up channels for calcium to enter in and as I said before, if you increase calcium, you increase exocytosis of neurotransmitters, and then you can send a synapse down the neuron to the brain. Okay, finally we have our sour taste cell for hydrochloride. And so with hydrochloride, you're gonna have protons that will go through a channel, depolarize it, increase or open up a channel for calcium to get in, and then with calcium you send out neurotransmitters and an action potential. And you also have ligands that can do that as well. So you have protons that are diffusing across the membrane, as well as ligands that will attach and help it to depolarize, allowing calcium in. Another thing to keep in mind is like the innervations of your tongue. So these are your primary gustatory neurons, the ones that immediately follow your taste cells. But then on your tongue, there's going to be certain innervations that will take it all the way to the brain. And that's going to be your facial nerve, your glossopharyngeal nerve, as well as your vagus nerve. The facial nerve is going to innervate the first 2/3 of your tongue, like the front half. And then your glossopharyngeal nerve is going to get the back third. That's kind of where your pharynx is. It's back there, right? And then your vagus nerve is going to innervate your pharynx almost entirely. So that's something to keep in mind with taste and how we stimulate taste cells with different tastings. Okay, let's move on to smell. So first off, we have our nose right here. That's kind of rudimentary for a nose, but we breathe in things, and these are chemoreceptors. You'll have chemicals in the air that you breathe in. And so what's that gonna do? Well, we have a couple things right in our olfactory area, and you'll have an olfactory bulb right above the bone, above your sinuses or nasal canal. And right above the bone, and then below that bone you'll have the olfactory epithelium. And so your olfactory bulb is going to house mitral cells. Mitral cells being essentially what sends the signal back to the brain. And then you're going to have a glomerulus, which is kind of a webbing of a bunch of nerves. And then that glomerulus is going to be attached to your olfactory neurons. And so olfactory neurons being housed in your olfactory epithelium, the glomerulus stretches through the bone, and your mitral cells and your glomerulus are housed in that olfactory bulb. So that's kind of the layout or anatomy of the olfactory system. And for humans, that can be an area of only about 10 square centimeters, which isn't huge, but it houses these cells. How does this all work? How do we get a signal to go? Well, first off, all of these olfactory neurons are G protein coupled receptors. If you have a chemical that attaches to those receptors, then that will stimulate adenylyl cyclase. Adenylyl cyclase will then stimulate cyclic AMP, and what cyclic AMP will do is it will open channels in these receptors that allow in sodium and consequentially depolarize and allow in calcium, much like in our taste receptors. You depolarize, you allow calcium in, you send off neurotransmitters. This also can have another effect where you can open it up such that chloride ions leave the receptors, and that further depolarizes it. So you're just sending off another signal. And that's how smell works. And yeah, that's chemoreception of smell and taste.